Okay, shall we start? Alright, so this is the discussion for March 11th, and it's um, the first time we do that, so let's see how that works. Okay, so first problem, we fix a positive number alpha, and we pick x1 greater than square root alpha, and define the rest of the x's recursively by xn plus 1 equals 1 half xn plus alpha over xn. Okay, so part A of the problem, prove that the sequence xn is monotonically decreasing, and the limit of xn as n goes to infinity is equal to square root of alpha. Okay, so how do we do this? So what do we know? First, by just looking at that, we can see the sequence is always positive because square root alpha is a positive number. X1 is positive, so you plug X1 into this, you can see X2 is positive. And if X2 is positive, then X3 is positive, so on and so on. Okay, and then what else do we know? We know that X1 is greater than alpha. Okay, so let's say suppose xn is greater than square root alpha, then what do we know about xn plus 1? So here's what we can do. So we want to show, so the idea is to show if xn is greater than square root alpha, then xn plus 1 is also greater than square root alpha. So how do we show this? We compare xn plus 1 square and alpha. So we take their difference and we want to show the difference is positive. Okay, so how do we do this? Well, we take this observation. By definition of xn plus 1, xn plus 1 squared minus alpha is equal to 1 over 4 xn minus alpha over xn squared. Okay, so to see this, so this is xn plus 1, so we square that, we have 1 over 4 xn plus alpha over xn squared, right? So this is xn plus 1 squared. So we expand the parentheses, that's 1 over 4 xn squared plus 2 alpha plus alpha squared over xn squared, right? Now if we subtract an alpha from there, so you can see xn plus 1 squared minus alpha would be 1 over 4 xn squared minus, so here is 1 over 4 times 2 alpha, so that's in fact 1 over 2 alpha. So if we subtract an alpha from there, that's minus 1 over 2 alpha. So minus 1 over 2 alpha is equal to 1 over 4 times minus 2 alpha. So here we put minus 2 alpha there, and plus alpha squared over xn squared. Okay, and then you realize this is 1 over 4 xn minus alpha over xn squared. Okay, so it's something square, therefore it's always greater than or equal to 0, so that shows xn plus 1 square minus alpha is positive or no negative, so that implies this, which implies xn plus 1 is greater than square root of alpha. So what we have shown here is if xn is greater than square root alpha, then xn plus 1 is also greater than square root alpha. Now, since x1 is greater than square root alpha, so by induction, everything is greater than square root of alpha. Okay, so we showed it's bounded by square root of alpha. So we haven't shown it's monotonically decreasing. So how do we show that part? So to show it is decreasing, we take the difference. So this is equal to, so you just use the definition of xn plus 1, right? So this is xn minus 1/2 xn plus alpha over xn. So that's, what is it? That's 1/2 xn minus alpha over xn. Okay, so now we know xn is greater than alpha, square root of alpha. So this is greater than square root of alpha, and this would be less than square root of alpha. So you can see the difference is positive. Okay, so that shows xn is greater than xn plus 1. Okay, so our sequence is decreasing. Okay, so now what about the limit? So here we showed square root of alpha is a lower bound, but lower bound doesn't mean it's the limit. So think of this example. Here you have a bounded monotone sequence. Okay, so it's decreasing, but its limit may not be the lower bound. So there could be a gap here. So we still have to show square root of alpha is the limit of the sequence. So how do we do that? Well, suppose the limit is lambda. Limit equals to lambda. Then by this relation, we must have lambda equals 1/2 lambda plus alpha over lambda. Because as you can imagine, if this sequence converges at all, which we know it does, it's a bounded monotone sequence, so it converges. Then if n is big enough, xn plus 1 and xn are both very close to the limit. The limit is lambda, so we necessarily have this relation. And then you solve for lambda. And how do you do that? Well, you can multiply both sides by lambda, and then you get a quadratic equation. So we all know how to solve a quadratic equation, and then we know the limit has to be positive because every term in the sequence is positive. So you just take the positive root of this quadratic polynomial, and then you will see a root for this equation is lambda equals square root of alpha. Okay, so that concludes part 1, part A. Okay, so now how about part B? Okay, so let's erase this. Okay, so part B. Part B, put epsilon n to be xn minus square root of alpha, and show that epsilon n plus 1 equals to epsilon n square over 2xn, which is less than epsilon n square over 2 square root of alpha. Okay, so really we only have to show this part, because part A, we know that xn decreased to square root of alpha, right? So 2xn is bigger than 2 square root of alpha, so this is automatic, follows from part A. Okay, so how do we show this inequality right here? Let's see, so what is epsilon n squared over 2xn? So we use the definition of epsilon n squared, or epsilon n, so that's xn minus square root of alpha square over 2xn. Okay, then we expand the parentheses. That gives us xn squared minus 2xn times square root of alpha plus alpha over 2xn. Okay. Then what do we have? So xn squared divided by 2xn, that gives us 1/2 xn. Okay, and then there gives us minus square root alpha, and then plus 1/2 alpha over xn. Okay, so we can further rearrange this. So this is 1 over 2xn plus alpha over xn minus square root alpha, right? So why do I put it this way? Because we realize this is equal to xn plus 1 by definition here. So this is xn plus 1 minus square root of alpha, which by definition is epsilon n plus 1. Okay. All right. And then let me write over here. So this part B is not quite finished yet, because we have a part B of part B, which says let beta equals to 2 square root of alpha, then we show epsilon n plus 1 is less than beta times epsilon 1 over beta to the 2 to the n. Okay. All right. So how do we do that? So first from here we can see that epsilon 2 is less than epsilon 1 square over 2 square root alpha, right? So that's epsilon 1 square over beta. Okay, because we proved this part, I'm simply letting n is equal to 1. All right, and then what do we do? Then we can prove by induction. So this is our base case. And then use induction. So we suppose epsilon n plus 1 is less than beta epsilon 1 over beta to the 2 to the n, and then we want to show we want epsilon n plus 2 is less than beta epsilon 1 over beta 2 to the n plus 1. So how do we do that? Well, epsilon n plus 2 by this relation is less than epsilon n plus 1 square over beta. right? So, and then we use the induction hypothesis that's less than beta square epsilon 1 over beta. Now we are squaring epsilon n plus 1. So if you square something, your exponent gets multiplied by 2. So 2 to the n times 2 is equal to 2 to the n plus 1. So that's 2 to the n plus 1. Okay. And then what's next? Oh, there's a divide by beta, right? So beta square cancels beta. Okay, so that's exactly what we want to show. Okay, so part B is done. All right, okay. So what is this question doing? So let me erase some of this. So let's see. So you can think of this as a way to approximate square root of alpha. So think of you are using your calculator, right? So we all know that the numbers from the calculator are not exact. So you cannot express, say, square root of 2 exactly in your computer. So they have to approximate it, right? So they need a fast algorithm to approximate, say, a square root of a prime number. Okay, so how will they do that? So this is exactly what they do. So they produce a sequence of numbers that can be proven to approach square root of alpha. So how good is the approximation? That's where you look at the epsilon n. So epsilon n is the difference of xn and square root of alpha. So we want epsilon n to go to 0 very fast, right? So recall what we just showed is epsilon n plus 1 is less than beta epsilon 1 over beta to the power of 2 to the n, okay? So as long as your initial guess is not too far off, so if epsilon 1 over beta is, say, less than 1, then this thing goes to 0 super fast. In fact, it's even faster than exponential rate because your exponent is exponential in n. So this is a super fast, you can say, algorithm for computing the square root of some number. Okay, moving on to next problem. So now we have a Cauchy sequence, say Pn, in a metric space X. Cauchy sequence in a metric space X, and some subsequence of xn converges to a point. So some subsequence of Pn goes to P in X. Then we want to prove that the full sequence also goes to P. Okay, so what do we want to show? So we want to show, given any epsilon greater than 0, there exists an n such that if n is greater than n, then the distance, so here I'm using d for a general metric, so the distance between Pn and its limit is less than epsilon. Okay, so by now you should be very familiar with the definition of convergence of a sequence. Okay, so that's our goal. Okay, so what do? We know the subsequence goes to P, right? And Pn is a Cauchy sequence. So here's the idea. Okay, so you have a sequence. Okay, so say that goes to, you want to show that goes to P, and you have a subsequence, say this is your subsequence, then you know it's going to be very close to P eventually. Say this is P. Let's say after this point, your subsequence is very close to P. Okay? Now, because Pn is a Cauchy sequence, so these points are very close to that. So this is close to P, and this is close to this. So by application of triangle inequality, you can show these points are also close to P. Okay, so now we have to just make it rigorous. So how do we put that into a rigorous statement? So we know Pn is Cauchy, so we can choose, say, n1 big enough so that the distance between Pm and Pn is less than, say, epsilon over 2 for m and n bigger than n1. Okay? And then we can choose n bigger than or equal to n1 such that the distance between P and K and P is less than epsilon over 2 if our say nk is greater than n. Okay? Then we just use triangle inequality. The distance between Pn and P is less than or equal to the distance between Pn and P, say, n plus d Pn and P, right? So this is less than epsilon over 2, right? Because n is greater than n1, and, oh, sorry. Now this is less than, yes, epsilon over 2 because of this, and this is also less than epsilon over 2 because of that. So you put them together, this is less than epsilon. Okay. Okay, next problem. Suppose we have two Cauchy sequences, Pn and Qn. So Cauchy in the metric space X, metric space X, we want to show that the sequence dPnQn converges. Okay. So to show this converges, it's equivalent as showing this is a Cauchy sequence. So why does this converge? Well, here's the intuitive explanation. So Pn is Cauchy sequence, so say that's Pn. So it goes to some point, say P, right? And we have another Cauchy sequence, say Qn. Okay, that converges to Q. Okay, so their distance, say this. So you'll see the distance converges to the distance between P and Q. Okay, so that's the intuition. How do we show that exactly? First, we write down this. So proof the distance between Pn and Qn is bounded by the distance between P and PM plus distance between PM, QM plus the distance between QM, QN. Okay, so this is the distance between PN and QN. So this is saying we go from PN to say PM, and then PM to QM, and QM to QN, right? So this expression on the right hand side, you can think of it as the distance of this path, which is of course greater than the distance of the direct path. Okay, so this follows from triangle inequality. Okay, so Pn goes to P, right? So Pn is Cauchy sequence, so this goes to 0, right? And this also goes to 0. Okay, so we have dPn Qn is less than or equal to, well, we can say this is, say, epsilon over 2, epsilon over 2. So that's less than or equal to epsilon plus dPm Qm, right? And then we switch the role of n and m. You can show dPm Qm is less than or equal to epsilon plus dPn Qn, right? So that together implies the distance between these two is less than epsilon, right? So you can always choose n and m big enough, so this is less than epsilon over 2, and this is less than epsilon over 2, right? And then you do this, you switch the role, you have that, and this is saying this sequence is Cauchy sequence. So Cauchy sequence of metric space converges. Okay, next we first introduce an idea called grouping. So what is a grouping of a series? Say this is our series, 1 minus 1/2 plus 1 over 3 minus 1 over 4 plus, say, 1 over 5 minus 1 over 6 plus 1 over 7 minus 1 over 8 plus da da da. Okay, so this is the series sum 1 over n times minus 1 to the n plus 1, right, as n goes from 1 to infinity. Okay, so let's call this sum xn. Okay, so xn is equal to this. Okay, now we take a grouping of the series. So we group these two terms together, these three terms together, da da da, and let's call the series sum y to the y sub n. So y1 is equal to 1, y2 is minus 1/2, and y3 is 1 over 3 minus 1 over 4, and y4 is equal to 1 over 5 minus 1 over 6 plus 1 over 7, etc. So this is a grouping of the original series, and we want to show the following. If a series sum xn is convergent, then any series obtained from it by grouping is also convergent. n converges to the same value. Okay, sounds intuitively obvious. So let's actually prove that. So say y1 is equal to x1 plus plus x sub k1. So this is x1, x2, x3, x4, xk1, and then next we have xk sub 1 plus 1 plus all the way to xk sub 2. Say this is our first term and this is our second term. So y2 would be xk plus k1. So xk1 plus 1 plus all the way to x sub k2. Okay, so let Sn denote the nth partial sum of xn. So this is sum, say xi, I from 1 to n. Okay, and tk denote the partial sum of yj, so j from 1 to k. Then we have t1 by definition is equal to y1, which by definition is equal to sk1, right? And t2 is equal to y1 plus y2, which is by definition equal to sk2. Okay? So what do you observe here? You observe that the sequence, say t sub k, is a subsequence of s sub k, or s sub n, right? So this is a convergent sequence because the series is convergent, meaning that the sequence of partial sum is convergent. So the subsequence of a convergent sequence is convergent and converges to the same limit. So subsequence of a convergent sequence converges to the same limit. Okay, that's that. All right. Good. So next we introduce another concept called rearrangement. Rearrangement. So just as the name suggests, so say let's look at this series, say 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5, A rearrangement would be something like 1 plus 1 over 3 plus, say, 1 over 8 plus 1 over 2 plus 1 over 4. So you just switch around the position of your terms. Okay, that's a rearrangement. And the formal definition, a series y sub k, sum y sub k in R is a rearrangement of some xk if there is a bijection. Bijection, say f of n denotes the set of rational natural numbers. Bijection of n to n such that y sub k is equal to x f of k. Okay, so f of k, f is a bijection, so f of k is another natural number. Okay, so every term of the series in y is some term in the series xk for k in n. So you just permute them. Okay, now next we have the theorem called the rearrangement theorem. So what does it say? Let some xn be an absolutely convergent series in R, then any rearrangement sum of yk of sum of xn converges to the same value. This should be no surprise, right? Because if your series convergent, you permute the terms, it's still going to be convergent because eventually all the terms are going to be summed. Okay, so let's see, how do we prove that? Say, suppose the limit of the series is equal to x, then, well, let Sn be the nth partial sum. So that's x1 sum all the way up to xn. Then, given any epsilon greater than 0, by definition, there exists an n such that if, say, q is greater than n, and if q is greater than n, then well, let's say n and q greater than n, such that if nq greater than n, then the difference between x and Sn is less than epsilon, and sum of k from n plus 1 to q xk is less than epsilon. Okay, so let's see, why is this true? So this part should be no surprise, right? Because the sequence of partial sum converges to x. Now, how about this part? Well, this follows from the assumption that our series is absolutely convergent, right? So, so you can think this is our terms. So absolute value of x1 plus absolute value of x2 plus, say, absolute value of xn plus da da da. So this is a convergent series, right? Because it's absolutely convergent. So there exists an n such that these going to be very small, right? So this is exactly what this is saying. So you can take a part from here and they will be very small. Okay. Then what's next? So we'll let m in n be such that all of the terms say x1 to xn is contained in y1 plus all the way up to ym, right? Because this big N is a fixed number, right? So given any fixed epsilon, this big N is fixed, right? So there's only finitely many terms here. And because the series is a rearrangement of the original series, right? So if you choose n big enough, eventually y1 plus all the way up to yn would include all these things here. Okay? Then it follows that, okay, so this, okay, so let's define this to be Tm. Then it follows that Tm minus Sn Tm minus Sn, the difference would be less than epsilon, right? Because what are the difference? So the difference would be those yi's that are not in here, right? So these would be terms from here, and those are negligible, right? So you would have, so if m is greater than m and n is greater than n, we must have Tm minus x is less than or equal to Tm minus Sn plus Sn minus x, right? So this is less than epsilon plus epsilon, that's 2 epsilon. So this is triangle inequality. This we just argued would be less than epsilon, and this would also be less than epsilon because of this. Okay, so that shows the sequence of partial sum of those y's also converges to x. Okay, so that's that. We are done. All right. So for some of you, maybe the only surprising part is why do we need this absolute convergent condition? Because intuitively, because a plus b equals to b plus a, right? So if you rearrange those summands, it should not affect the final limit. But here is why we need this absolutely convergent condition. So if x, say sum xn is not absolutely convergent, so it's not absolutely okay, so if it's divergent, then obviously sum of yn could also be divergent, right? So let's say it's not absolutely convergent, but convergent, or conditionally convergent. Okay, and let sum of yn be a rearrangement of sum xn, then I claim sum of yn can be anything, even, plus, or minus infinity. Okay, how could that be the case? Because, so here's the idea. Sum of xn is conditionally convergent. Right? So some of the terms are positive and some of the terms are negative. And if you just sum up all the positive terms, it goes to infinity, right? And if you sum all the negative terms, it goes to negative infinity, right? Okay, so we can take out all its positive terms. So let me denote this, and all its negative terms. Okay, so this is minus infinity, this is plus infinity. Okay, now this is a rearrangement. I claim this can be anything. Okay, so here's the graph. All right, say I want this series to converge to L. Okay, so I start with 0. Okay, then I start to sum up all the positive terms. Okay, so this this is S1 and this is S2. So my sequence partial sum will start to increase, right? Because I'm summing those positive terms. Okay, so once it crosses L, what I'm going to do, I'm going to start to add those negative terms so that it crosses the L again. Okay, and then once I go past through L, I'm going to again start to sum those positive terms. And then once I pass L, I start to add negative terms. Okay, so on and so on. And you can see that this converges to L because because my series is absolutely convergent, right? So the magnitude of those terms will eventually go to 0, right? So I can always make sure that I stay close to L, as close as possible, or as close as I would like, right? So you can see it goes to L. Okay, so L could be anything because they goes to positive infinity or negative infinity. Okay, so that's why you see the absolutely convergent condition is absolutely necessary. Okay, so next we're going to show a interesting example. So here I define aij to be 1 if I minus j is equal to 1, and aij is equal to minus 1 if I minus j is equal to minus 1. And then we consider this iterated sum. So sum from I to 1, I from 1 to infinity, sum j from 1 to infinity, aij. Okay, so what does it mean? So really, what it means, you just think of this, each of this as a number, and it is summing up with those numbers, and these are evaluated as a series, sum of a series. Okay, so we want to show this is not equal to the following. So j from 1 to infinity, I from 1 to infinity, aij. Okay, so what I did here, I switched the order of summation. Okay, let's see why they are not equal. So let's first look at the term on the left-hand side. Okay, so let's say if I is equal to 1, what is sum of j to infinity aij? So remember, I is equal to 1. Oh, I should say aij is equal to 0 otherwise. Okay, so this is equal to a11 plus a12 plus a13 plus a14 da da da. So a11 is equal to 0, right? What is a12? A12 is equal to minus 1, right? Because 1 minus 2 is equal to minus 1. Okay, so that's minus 1, and that's 0. That's 0. Okay, so this is equal to minus 1. Now, if I is equal to 2, then sum j from 1 to infinity, aij would be a21 plus a22 plus a23 plus a24. Da, da, da. So we'll see that a21 is equal to plus 1, and a23 is equal to minus 1, and the rest of the terms are 0. Right? So this is 0. And similarly, you can see if I is equal to 3, this sum is also 0. So in fact, the thing on the left-hand side is sum I from 1 to infinity or really it's just minus 1 plus 0 plus 0 plus 0, right? So the result is minus 1. Now how about the thing on the right hand side? So let's see, we first evaluate sum aij I from 1 to infinity. Okay, say when j is equal to 1, this is equal to a11 plus a21 plus a23 so a11 plus a21 plus a31 plus a41 so a21 is equal to 1, right? So this is equal to 1 and the rest are 0, so that's 0 0 0. And if j is equal to 2, and then the sum aij would be, so this is equal to I from 1 to infinity. So that's a12 plus a22 plus a23 plus da da da. And this is equal to minus 1, this is equal to 1, right? And the rest are 0. So minus 1, 1 cancel out, so this is 0. So as you can see, for all the other j's, this sum is equal to 0. So the term on the right hand side, sum j from 1 to infinity, sum I from 1 to infinity, aij, would be 1 plus a bunch of zeros. So the answer is 1. So you can see these two are not the same. So the moral of the story is you cannot switch summations. Okay? So when can you switch summations? If let me write this. If this is convergent, then it is okay to switch summations. Okay, in other words, we still need absolute convergence. So let's recall a theorem we know from Calc 3 called Fubini's theorem, right? What does it say? So it says in some cases you can switch the order of integration, right? So when can you switch the order of integration? You can do that if this is well defined, right? So this, you can think of it as a discrete version of Fubini's theorem because there is no essential difference between summation and integration. Okay? Okay, next problem. Determine the convergence or divergence of the series sum an, where an is equal to 1 over n plus 1 times n plus 2. Okay, so how do we do this? One thing we can do is limit comparison test. Okay, so limit comparison test with 1 over n squared. We know that sum of 1 over n squared converges, right? So if the ratio of the nth term is going to some fixed number not equal to positive and negative infinity, then they both converge. So we'll do this. Limit as n goes to infinity, 1 over n plus 1 times n plus 2 divided by 1 over n squared. So that's limit as n goes to infinity, n squared over n squared plus 3n plus 3. And then we divide both numerator and denominator by n squared. We have 1 over 1 plus 3 over n plus 3 over n squared. Now you let n goes to infinity, this goes to 0, this goes to 0, so the limit is 1. Okay, so by the limit comparison test, they converge. So next, how about an is equal to n over n plus 1 times n plus 2? Okay, so again, we do limit comparison with which series? We compare that with sum 1 over n. Okay, so here's the intuition. Your numerator is degree 1 polynomial in n, and your denominator is of degree 2, right? So your numerator is of this order, and denominator is of this order. So if you take the ratio, it is of order 1 over n. So that's why we compare with 1 over n. So we know the sum of 1 over n is equal to infinity, okay? So we take limit of the ratio, then this is equal to limit as n goes to infinity, n squared over n squared plus 3n plus 3. So again, we divide numerator and denominator by n squared. So that's a square. We have 1 over 1 plus 3 over n plus 3 over n squared. So again, this limit is equal to 1. So either they both converge or they both diverge. Since this is divergent, this is divergent. Okay, next, an is equal to 2 to the minus 1 over n. Convergent or divergent? In fact, this is divergent. Why? Because we take limit as n goes to infinity, 2 to the minus 1 over n. So that is equal to 2 to the 0, which is equal to 1, right? So the term does not go to 0, therefore it diverges. Okay. Next, an is equal to n over 2 to the n. So whenever we see that n is in the exponents, we can use root test or ratio test. Okay, so we can do, say, ratio test. Then we need to evaluate the limit of the ratio. So that would be n plus 1 over 2 to the n plus 1 times 2 to the n over n. Okay. So these two cancel and there will be a 2 left. That would be n plus 1 over n times 2. Okay. Then you take limit as n goes to infinity. You can divide both numerator and denominator by n. So we have 1 plus 1 over n over 1 times 2. And the limit is equal to this should be 1 over 2, right? Because the 2 is on the denominator. So that's 1 over 2, which is less than 1. So by the ratio test, this series is convergent. Okay, so next example, probably a little tricky. We'll determine the convergence or divergence of the series. Sum an, if an is equal to log n to the power of minus log n. Okay. All right. So how do we do this? Well, we first consider 1 over an. So 1 over an is equal to log n to the power of log n. Okay. Now we have log n on the exponent. That's a little annoying. So what do? We can take log. Okay, so log of 1 over an is equal to log of log n, so log n times log log n, right? So here I'm using this. So log of a to the b is equal to b times log a. Okay, so now log n, the exponent, is now in the front. And for n big enough, this is going to be greater than 2 log n, right? Because log n goes to infinity. So this is going to be greater than 2. So this log n is the same as the log n over here. Okay. So what do we do next? Now we have log n times log log n greater than 2 log n, right? So if we put e over here, it's still going to be true, right? So that shows. So this is what? This is equal to log n so it's log n to the power of log n, right? Because how do we get this? We take the log and then we exponentiate that. So we get back to the original thing. So this is going to be greater than e to the 2 times log n. So that's e to the log n square, which by definition is n square, right? Okay. So this implies log n to the power of minus log n, I'm taking the reciprocal, is less than 1 over n squared. Now, since this is convergent, it follows that this is also convergent, okay, by comparison test. All right. Okay. So let's look at next the convergence of this. An is equal to n log n inverse. Okay. So for this, we can use integral test. We consider the integral of x, 1 over x log x dx, as x goes from 2 to infinity. Okay. We cannot x goes from 1 to infinity because log of 1 is equal to 0. We are dividing by 0. That's not good. Okay, so this, how do we value this integral? We can use a u substitution. So recall that the derivative of log x is equal to 1 over x, right? So you can let log x be u. So this is the integral, let's say x from 2 to infinity, right? U, 1 over u du. Right? Okay, so you integrate 1 over u, you're going to get log of u. So log of u is equal to log x, right, from 2 to infinity. So as you can see, if you plug it into infinity, you got infinity. Okay? So by the integral test, this is divergent. Okay. Okay, a few more examples should be less tricky. Okay. So this time an is equal to 2 to the n times e to the minus n. Okay, so we can use root test, limit as n goes to infinity, absolute value of an to the 1 over n. So that's limit as n goes to infinity. So what's the nth root of this? It's going to be 2 over e, right? Which is less than 1, so it converges. Next, an is equal to n to the n times e to the minus n. Okay, so this 1 over n should be outside. Again, root test. So we take the nth root of an, so that's n over e. And then you let n goes to infinity, this goes to infinity, so it is divergent. Okay. So next, an is equal to e to the minus log n. Well, this by definition is e to the log n to the minus 1. So that's n to the minus 1, right? So we're essentially looking at this series, which we all know is divergent. Okay. Next, an is equal to log n times e to the minus square root of n. Okay, so how do we do that? So this is log n over e to the minus e to the log n, right? And we know this is less than n over e to the power of square root of n, right? Because n grows much faster than log n. From here, it's probably already obvious to you that this should go to 0 pretty fast, almost exponentially fast. But we still need to prove that. So claim e to the square root of n gonna be greater than, say, n cubed. Okay, so claim as n go to infinity, then this would be less than n over n cubed, which is 1 over n squared, and we know this is convergent. Okay, so now our goal is to show that this is true. So what can we do? We can look at the ratio, say n cubed over e to the square root of n. Okay, so this is infinity over infinity. You can use L'Hopital's. Then you have limit as n goes to infinity as 3n squared over, what's the derivative of this? So recall the derivative of this would be 1 over 2 square root of n e to the square root of n. Okay, so again, it's infinity over infinity, so you use L'Hopital's again. Let me rewrite this. So that's going to be 6n to the 5 over 2 over e to the square root of n. So as we can see now, originally we start with n cubed. Now it is n to the 5 over 2. So you do L'Hopital's again. Okay. You keep doing L'Hopital. Each time you do a L'Hopital, the power is going to decrease. Okay. Eventually you decrease it to some constant. So you keep doing that, and then you can show this is equal to 0. Okay, so the L'Hopital is left as an exercise. Okay. Next, an is equal to n factorial times e to the minus n. Okay, whenever you see factorial, it's a good idea to use the ratio test. So that's going to be n plus 1 factorial over e to the minus, times e to the minus n plus 1 over n factorial times e to the minus n. Okay, so the ratio, if you simplify, that's going to be n plus 1 over e, and that's greater than 1 because n is going to infinity. Therefore, by the ratio test, this is divergent. Okay, so next, n factorial times e to the minus n square. So again, we see factorial. We're gonna use the ratio test. Okay, and then you simplify, you're gonna have n plus 1 over e to the 2n plus 1. Then you take the limit. So let me write the limit everywhere. As n goes to infinity. Okay, so you use L'Hopital, right? You're gonna have 0. Okay, so by the ratio test, this is convergent.